Up until now, we've only ever looked at the overall mean of a continuous variable, like the mean height for the entire class. However, we often want to estimate the means within levels or categories of another variable. For example, we may want to look at the mean height within levels of gender. Said another way, we may want to know the mean height for men and separately the mean height for women. More generally, in this video you will learn to perform bivariate analysis when the outcome is continuous and the predictor is categorical. Typically, in a situation such as this, all we need to do is apply the analytic methods we've already learned from a single continuous outcome, but apply them separately within levels of our categorical predictor. Watch as I demonstrate how this is done using SAS. To start with, we'll again use our class survey data. We can estimate these statistics in SAS using the means procedure with either a by statement or a class statement. Choosing which to use is somewhat arbitrary. As we previously learned, before you can use a by statement, the data must be sorted on the by variable. The class statement does not require you to first sort the data. However, the by statement is computationally more efficient than the class statement. Also, the appearance of the output is slightly different depending on whether you use a by statement or a class statement, so you may have a preference. But the datasets we are using in this class are relatively small, and I like to program with the fewest number of steps possible, so I'll be using the class statement. Here we're using the means procedure to calculate height within levels of gender. When we run proc means with a class statement, SAS produces a table of statistics with separate rows for males and females. The statistics shown by default are the total number of observations within each level of gender, the number of non-missing for the variable height observations within each level of gender, and then the mean, standard deviation, minimum value, and maximum value. As you look over this table, you should have an idea of whether males or females in the class appear to be taller on average, and whether males or females in the class appear to have more dispersion around the mean on average. We can also use a format in our means procedure to group or regroup variables for use in a class statement. For example, let's say that we want to calculate the average salary separately for students who are under age 30 and students who are age 30 and above. Here we're creating a format that once applied will display all ages up to 30 as younger than 30 and all ages greater than 30 as 30 and older. Then in the means procedure we can apply the format to our class variable. And when we look at the results viewer window, we see that the procedure produces the requested statistics within levels of age group defined in the format. We can also see that it pays to get older, literally. Using this method will allow you to easily experiment with different groupings of class variables without creating new data sets. Another important statement to learn is the output statement. In this context, the output statement allows you to create a new data set that contains the results of the means procedure, as opposed to just a report of the means procedure. The nice part is that these statistics can be saved and used for further analysis. In this means procedure, we're requesting the default statistics for height and weight within levels of gender. But this time we want to add an output statement. The keyword out equals tells SAS what to name the new dataset. Then we specify the statistics that we want to include in the new dataset. Following the equal sign, we can give a list of variable names that correspond to the statistic. In this case, we're requesting the mean and telling SAS to name the new variables in the dataset mean HT and mean WT. I also used the no print option in the proc statement. This tells SAS not to report the results of the means procedure in the results viewer window. Instead, we'll view the dataset we just created using the print procedure. And here is our new dataset. By default, SAS puts the mean for men and women combined, sometimes called the grand mean or marginal mean, in the first row of the dataset. We aren't going to discuss the type variable in this lecture because it doesn't affect the interpretation of your results. However, feel free to Google it if you're curious. The important thing here is that now you can not only view the mean by gender, you have the information stored in a new data set that you can use for further analysis. For example, you can now plot the mean values on a graph. This next example is pretty much the same. I'm just going to use it to demonstrate two additional points. First, you can output almost any statistic that you can request in the means procedure to the new data set. The second is a nice little statement option called AutoName. This will name the variables in the new data set in a logical way for us. Because it is a statement option, as opposed to a global or step option, it's put at the end of the output statement to the right of a /. Viewing our new data set, we can see that all the requested statistics are there, and named in a consistent and easy to understand manner. And what if you want to generate a report of statistics within levels of 2 or more variables? You can do that by adding additional variables to the class statement. Here we're requesting the mean, standard error, and 95% confidence intervals for the mean of BMI within levels of gender and age group. And we can see these statistics for BMI within levels of age groups separately for males and females. Males that are 30 and older report, on average, the highest BMI. Females age 30 and older report, on average, the lowest BMI. This is good information, but often when comparing groups, a picture really is worth 1,000 words. Here we're using SGPanel for the first time. It works much the same as SGPlot, but it allows us to create a panel of graph cells for the values of one or more class variables. The panel by statement allows us to specify the class variable whose levels will be divided into panels. This will make more sense soon. Then we tell SAS that we want a vertical bar chart with the VBar statement, and that age should define the categories for the bars. Ordinarily, this would be a mess. There would be a different bar for every value of age. But because we've categorized age into age groups, above and below 30, using a format, there will only be 2 bars per panel. The response option specifies a numeric response variable for the plot, in this case BMI. The stat option specifies the statistic to be displayed on the y-axis, in this case the mean. The limit stat option specifies the statistic for the limit lines. In this case, we specify the 95% confidence limits for the mean with the keyword CLM. And there is our vertical bar chart depicting mean BMI with 95% confidence limits by age and gender. As you can see, our data don't allow us to confidently state that there is any difference in BMI by age group and gender. Just like we can use a class statement to produce summary reports in proc means over levels of a class variable, we can produce univariate reports and plots using proc univariate with a class statement. In this example, we're producing univariate reports for height over levels of gender. And because we're using the plot option, we will also generate a histogram, box plot, and QQ plot within levels of gender. Here you can see all the usual univariate statistics, first for females and below for males. Additionally, you can see the 3 plots produced by default with the plot option. This is nice, but suppose you really want to compare histograms or box plots. Having to scroll up and down between pages is not the most convenient way to do so. In this first example, we're making side-by-side histograms using proc SGPanel again. Here we're telling SAS that the plot type is histogram and the variable we want a histogram of is height. We're also telling SAS to overlay a normal density curve on each histogram. And there are our side-by-side histograms. What do you think? Does height appear normally distributed in females? Does height appear normally distributed in males? Finally, here we use proc SGPlot to create side-by-side box plots. This is the same proc SGPlot you've already used to create a box plot, but this time the category equals option is used in the VBox statement. As you've probably guessed, the category equals option specifies the categorical variable you want to create distinct box plots for. And there are our side-by-side box plots. This plot makes it really easy to quickly make a comparison between males and females. Side-by-side plots like these are a great way to get a feel for the relationships between variables in your dataset. Now you practice describing the relationship between a continuous outcome and a categorical predictor. In this video, you learned how to numerically and graphically describe the relationship between a single categorical predictor and a single continuous outcome. You also learned how to save your results to a new SAS dataset. In the next video, you'll learn how to describe the relationship between 2 or more categorical variables.